Now we're going to talk about the normal probability distribution. This is perhaps the most useful of all probability distributions out there. Not only does it work well at times with respect to characterizing a population of interest, but it also can be used in other situations when a population doesn't follow a normal distribution. We won't talk about that second application right now, and we will postpone that until a little bit later in the course. What we are going to do right now is we're going to focus on those situations where the normal distribution does work for a particular population. And this is what the normal probability distribution function looks like. F of y is equal to this quantity here. Now, if you notice inside the quantity, we have a sigma and a mu, and that is not a misprint. The way that this particular probability distribution is written is so that the expected value of y, mu, is actually put into the distribution as a parameter that will control what the distribution looks like if it's plotted. Also, in this particular probability distribution function, we see sigma. That is the square root of the variance of y. And what that's going to do is control the shape of our plot of our curve of our distribution, as you will soon see. Now, in this function here, we have 1 over sigma times the square root of 2 pi, where that pi there is representing like 3.14. Then we have the exponential function, and we raise it to the negative y minus mu squared power divided by 2 sigma squared. This is defined for possible values of y that are between negative infinity and positive infinity. So, again, the expected value of y is equal to mu. The variance of y is equal to sigma squared. We'll look at how to find that shortly. Here is what a plot, kind of a crude plot of what the normal probability distribution function would look like in general when we're to plot it. So my x-axis, I have y. On my y-axis, I have the usual f of y. Now, the normal probability distribution function is centered at mu. And in fact, it's symmetric about mu. The highest point of this curve ends up being 1 over sigma times the square root of 2 pi. Well, why? Let's go back to the expression here. Notice if I were to put in mu for y there, I have mu minus mu squared, which would be 0 squared, or 0. E to the 0 is 1, and so this is what you're left with. That's always going to be the highest point of the curve when y is equal to mu. And as I said, the probability distribution, when you plot it out, it's actually symmetric about mu. How far out this part of the distribution goes corresponds to sigma. For small values of sigma, these blue lines will be drawn in. For large values of sigma, these blue lines will be drawn out. And also, I should have mentioned this before, the top of the plot will go down, because again, the area underneath that curve still needs to be equal to 1. We'll see some actual 2-scale examples showing this shortly. Now, the left and the right sides of the curve extend out to negative infinity and positive infinity without ever reaching f of y is equal to 0. Obviously, I can't draw out to positive infinity and negative infinity on my plot. Very often, and I've kind of used this terminology before, the far right sides, the far left sides of the distribution are referred to as the tails of the distribution. Let's see here. So let's actually look at some 2-scale pictures of the normal probability distribution function. Now, to evaluate f of y, I could simply program in the expression that I just had on the first page of this notes. Instead, what I can do is I can use the Dnorm function in R. We've seen functions like this before for other probability distributions. And its first argument is x, This is where you put in y, where you want to evaluate the PDF at. Let's say I want to evaluate it at 24.3. And then also have another argument, which is called mean. Suppose the mean was 24.3, just so that we can plot it. And then the next argument is SD for standard deviation. Let's say that sigma, my standard deviation, is 0.6. If I do that, then here is f of 24.3. Okay, so that would be the height of my curve at 24.3. Let's do some plots with that information now. So I can use the curve function I've done many times before. My expression of what I'm plotting is my f of y. So I can put Dnorm in there. And now I need to put in, okay, I want to plot it with respect to x. In other words, again, what R is going to do is put in a whole bunch of different possible values that would be on the x-axis of our plot, and then plot those points and connect them with a line. Mean 24.3, standard deviation of 0.6. I'm going to control my x-axis limits to be between 20 and 30. The distribution is going to be dark green. The line width is going to be 2, a y-axis label of f of y, x-axis label of y. So I'm going to do that plot, and then I'm going to add to the plot another plot, but now with the standard deviation 1.3, so that you can see the effect of what happens if that standard deviation changes. And that's going to be in blue. And what I'm going to do is in red, I'm going to add another plot where I have my original standard deviation is what I had originally. That's why it's called the original standard deviation. But I'm going to change mu to be 23.1. And then I'm going to put a nice legend on the plot to help us read it. And here's the plot. So the first probability distribution is in green. Okay, notice how it's centered at 24.3. Notice also it's very unlikely to have values corresponding to y outside of 22 and about 26.5 because the area underneath the curve there is very, very, very small. Now let's compare this to the plot that's in, or the line that's in blue. Same mean, but different sigma. Now sigma is going to be 1.3, so it's going to be larger. And again, what that means is my standard deviation is larger, so that means my possible values of y that I can observe in terms of what's probable, there's going to be a larger range of them. And we see that in that plot. Notice how far the blue extends out in this plot. So now it's quite likely to have values between about 20.5 and 28.5. Compare that to what we have for the green. But still, underneath that blue curve, I still need to have an area of 1. And so essentially what's happening is you can think of it this way. I'm going to put my hand on top of the green curve and kind of press down on it and maintain an area of 1 underneath that curve, and that causes the tails of the distribution to bow out. Now let's compare the green curve to the red curve. The only difference is now the mean changes. And so the plot looks exactly the same, except for the location of where it's at has moved to the left because 23.1 is less than 24.3. So because of that, mu is often referred to as a location parameter because it controls the location of where that distribution is going to be centered. Sigma is often referred to as a scale parameter because it actually helps to control how dispersed our possible values of y are. You know, what numerical scale do we expect, or what that's not necessarily the best way to put it, but you know, what again is the spread of the possible values of y. Okay, now very often you will see people write something like this, where let's say y has a normal distribution with a mean of mu and a variance of sigma squared for its corresponding random variable. Very often you will see people write that in a kind of a shorthand notation where we have a tilde there, even though at least on my screen it doesn't look very much like a tilde. That is a tilde. The tilde means the words as is distributed as. So y is distributed as, the capital N corresponds to normal. So people would read this as y is distributed as a normal random variable with mean mu, variance sigma squared. In other words, y can be characterized by a normal probability distribution where y has a mean of mu and a variance of sigma squared, whatever numerical value you're putting in there for that. Now, a very important special case of a normal distribution is what's called a standard normal distribution. That corresponds to mu equals 0, sigma equal 1. And you can see how things simplify corresponding to that. Very often, rather than, let's say, using x or y to denote the random variable, in this case, people will use a z. It's just kind of customary to do that, even though I didn't do it here. We will come back to the standard normal distribution later on. Now, the CDF, unfortunately, you can't really write it out very well, but a CDF still exists. So capital F of y is equal to the integral from negative infinity to y of f of t dt. To actually numerically find particular values of the CDF, we can use the Pnorm function. Again, compare that to what we've seen with other functions in R corresponding to the CDF before, where we always use P and then the name of the distribution, either the full name or abbreviation of it. As I mentioned before, the area underneath that curve is still equal to 1. Well, how could we actually show that? You could do the integration by hand, but let me warn you, it does take some time to do. So for our class, I'm okay if you just simply use Sage to do a integral like this. So to do that, then we can declare our what Sage would call variables, y, sigma, and mu. Sigma always has to be greater than 0. Remember, standard deviation is always the positive square root of the variance, and the variance is always greater than 0. Then I can type in, and you got to be very careful with all your parentheses, type in what that PDF actually would be. And then if I just simply ask to print it off, here we go. Let's find now the integral of f of y. I'm going to integrate with respect to y from negative infinity to positive infinity, and Sage gives me back square root of 2 times the square root of 1 over 2. For some reason, Sage cannot automatically simplify that to 1, so what can we do? We could save the results into a variable called int all, for the lack of a better name. And if we say int all dot simplify underscore full, Sage does do the simplification for us. Okay. Well, what about finding the expected value of y in the variance of y? Again, the integration here can be kind of complicated, so I'm okay with just doing it with Sage. So to find then the expected value of y, you take the integral of y times f of y. I'm integrating with respect to y, and I'm integrating from negative infinity to infinity. Put that into what Sage would call a variable called mu. And then with the simplify function, guess what? You get mu back. You could do a similar thing for the expected value of y squared. And then using the variance of y is equal to the expected value of y squared minus the expected value of y, that quantity squared, we get sigma squared back for the variance. Okay, so let's find some probabilities now with the normal probability distribution. And so we're going to go back to using a car miles per gallon example, where this time y is going to be a type of cars, its corresponding miles per gallon. We have a mean of 24.3 and a sigma equal to 0.6, like what we just saw a few pages in the past. Let's now find the probability that a car gets less than 23 miles per gallon. And so what does that look like? What are we trying to find? Well, here's our corresponding normal probability distribution here. You might note that it might look on your screen like the line's a little bit jagged. It's not supposed to be that way. It's just how I ended up getting the plots from R into Word. We had that, unfortunately, jaggedness appear. But this should be a smooth curve. Okay, so we've done plots like this. Please make sure you can do this yourself. In particular, how we can put this little line on top of the plot to represent that this is where 23 is, and we want to find then the area to the left of it. To do that line, you can use the segments function. Please see the corresponding program code. And so what we see in this plot is that this probability should be fairly small. If we got something that wasn't small, then you might be thinking, uh-oh, maybe I made a calculation mistake. So that's why it's always good to do a plot like this. So to find this area underneath the curve, what do we need to do? Well, we can integrate from -infinity to 23 my f of y dy. Obviously, a miles per gallon cannot be negative, but if we notice here on this plot that once that curve gets down to about the y-axis where y is equal to 0, we know that the probabilities are going to be extremely small down there. So that's why we can still use this PDF for this particular situation, even if a miles per gallon can't be negative. So how could we do this? Well, similar to previous sections, what we could do is create a function in R that has the PDF in it. And so that's what I did here. And then I can integrate, and I get 0.015, and notice how small that is. Also, one could go to Sage. Again, as we've seen, plug in the corresponding PDF. Notice now I evaluate mu and sigma at their corresponding values. Do the integral, and you get exactly the same result. But don't do it that way. Don't use Sage that way. Don't use R that way, because there's a much easier way to do it. Because notice what we're trying to find. The probability y is less than 23. In other words, we're trying to find the CDF evaluated at 23. And as we've seen with other probability distributions, there is a function in R that automatically finds or evaluates the CDF for us. And in R, it's Pnorm for the normal probability distribution. And so if I put in for the Q argument for quantile, 23, put in mu, put in sigma, I get that probability that I need quite simply, 0.015 again. So in other words, the 0.015 quantile from a normal distribution, in this particular case, is 23. Also, you will hear me say this a lot, and also other people say it too. When we have a continuous random variable like this, and we're using one of these p-like functions in R, excuse me, what the function is giving us is the area to the left underneath the curve. That's what we needed. That's what essentially the CDF is giving us with a continuous random variable. Well, let's say then we look at this case again where sigma is increased to 1.3. What would you expect to happen for y, the probability y is less than 23? You should be able to answer that without even finding the probability, or maybe even plotting it. Because again, my standard deviation is larger. So that means things will be more spread out. And so before, when I was on that extreme left side of that distribution, now that will not necessarily be as extreme as it was before, because now it's more likely to get values of y that are farther from the mean. And in fact, here's the corresponding plot. And we can see that indeed the area looks larger. And so if I use the Pnorm function again, change the SD argument value, I get 0.1586 as that corresponding area, underneath the curve. Well, let's go back to having sigma equal to 0.6 again. But now mu's decreased to 23.1. So notice how that location of that probability distribution is now moving over closer to where 23 is. And again, without even plotting, without actually even finding the probability, you should have an idea that, oh, this is going to be larger than what we had originally when it was 0.015. And indeed, here's what the plot looks like. If I use the exact same code, but now change the mean to 23.1, now I have an area of about 0.43 underneath the curve in that area. So here's a nice little diagram that actually compares all three of those situations. Okay. Now let's suppose that we want to know what's the probability that y is between 23 and 25. Okay. The easiest way to find this is to think again in terms of the CDF. I can break up this probability statement into two parts. The probability y is less than 25 minus the probability y is less than 23. In other words, the CDF evaluated at 25 minus the CDF evaluated at 23. Again, the function r that gives us that CDF is Pnorm. So I apply Pnorm twice, or I connect the two with a subtraction. And I get 0.86. And so the area underneath the curve right here is 0.86. Just to emphasize, in case I didn't say this before, all the code for these corresponding plots is in my corresponding program. Okay, so let's move on. Well, what's the probability now that y is greater than 23? Okay, well, let's think in terms of a complement first. Again, the probability of A is equal to 1 minus the probability of its complement. Here we can think of it as the probability of y is greater than 23 is equal to 1 minus the opposite of it. Y is less than 23. Well, what is that particular probability? Well, it's 1 minus the CDF evaluated at 23. And so if I go back up to where we had originally found that, .015, for some reason I couldn't remember what it was, then this is equal to 1 minus 0.015, or approximately 0.985. And again, go back to the actual plot, and yeah, it looks like that's going to be extremely large probability. It's going to be very close to 1. So it makes sense to have that. Well, what about now we look at what's the probability y is less than 23 or y is greater than 25? Okay, so it's either on the far left or it's on the far right. Well, again, what is the opposite of that? 1, so we can use, this is equal to 1 minus the probability now that 23 is less than y is less than 25. So that you're actually in the middle. And we had just found that probability to be 0.86. So it's 1 minus 0.86, or about 0.14. Now let's change things up. What miles per gallon is at least required for a car to be in that, let's say, the top 5% of all these types of cars? In other words, I want to find the value Q here such that the probability y is greater than Q is equal to 0.05. And also, in other words, what I'm actually looking for is the 0.95 quantile. In other words, the probability that y is less than Q is equal to 0.95 by using the complement. In other words, I want to use the CDF evaluated at Q is equal to 0.95. In other words, solve for Q. In terms of integration, this is what we're trying to do. Set 0.05 is equal to the integral from Q to positive infinity of f of y dy, or equivalently 0.95 is equal to negative infinity to is equal to the integral from negative infinity to q of f of y dy solved for q. Rather than setting up ways that we've looked at in the past to make this, to do this solve part here, there is actually a function r that automatically does it for us. And it's called the Qnorm function. Notice what we're trying to find, the 0.95 quantile from this normal distribution. So we use Qnorm, put in that probability in the p argument, 0.95, put in mu, put in sigma, you get 25.28. And again, does that make sense? Here's the plot, 25.28. Do have the area to the left of 0.95, the area to the right of 0.05? Yeah, it sure does look like it makes sense. What you will find that there are many other functions in R that also, for other probability distributions that have a name associated with it, that also have these Q-like functions. So for example, one that will that deals with what's called the gamma distribution, there is a Q gamma function associated with it. With another probability distribution called the T distribution, as in the letter T, there's a QT function with it. And we'll be using that kind of a function a lot later in our course. Okay, let's take a look at another example. You know, sometimes you hear about professors grading on the bell curve. Well, what does that basically mean? What that basically means is that they're going to scale all their grades corresponding to a normal distribution. So let's take a look at an example where that might be used. Let's say that mu is 73%, sigma is equal to 8% for some normal distribution. What could happen in actual application, although I would never do this, let's say a professor gave a test to, let's say, 100 students, and the sample mean was 73%, and the sample standard deviation was 8%. And in order to make judgments about what's an A, what's a B, what's a C, that professor says, I'm going to scale the distribution, the distribution of all grades to a bell curve. In other words, a normal distribution where they take that sample mean to be the population mean, take the standard deviation, sample standard deviation to be the population standard deviation. Again, I would not do that. But in some areas, you may see professors do that. So that we get used to working with this example, though, first, let's find the probability of receiving an A, 90% or higher for this particular probability distribution. So again, I can use the curve function, actually plot it, and we can see, unfortunately, there's a very small probability of getting an A. And in fact, if we, again, use the complement, 1 minus the probability of y is less than 90 is what we're looking for. In other words, 1 minus the CDF evaluated at 90. What we get then is 1 minus the P-norm function, or 0.0167, as that very small probability. Must have been a tough test. Anyway, what percentage of students score between a 70% and a 90%? So again, we can plot it out, and we can see that looks like that's a pretty large area there. And you know, the probability one particular student got between that grade level is equivalent to saying what is the percentage of all students within that grade level. And so we do what we just saw a few minutes ago. We break this interval up for this probability statement into two parts, so we can write this then in terms of our CDF. Once we do that, we can use the P-norm function with it, and we get an area of 0.63 approximately. Now we have a little bit of application of the bell curve then. Suppose that an instructor curves the test number 1 grades and only the top 10% of test scores receive A's. Would a student be better off with a test number 1 grade of 81% when we have a mu of 73%, sigma equal to 8%, or a grade of 68% on a different test with a mu of 62% and the sigma equal to 3%. So in other words, we want to see essentially where's that cutoff point for A's. And so what we're looking for now is the 0.9 quantile for both probability distributions. So we go to the Qnorm function. Here's the first probability distribution. The 0.9 quantile is 83.2. Now with that second test though, the 0.95 quantile, 0.9 quantile is 65.8. So again, we're given the choice. Would you want an 81% on that first test? Well, you end up with a B or something non-A, let's say. Or would you prefer a 65.84 on that second test? Would you prefer a 68% on that second test? Excuse me. Well, we know an A is 65.84 or above, so you would prefer that second test to get that A. Okay, let's go back to this rule of thumb for the number of standard deviations all data lies from its mean. When I first introduced this, I was talking about this was an ad hoc interpretation of Chebyshev's theorem or Chebyshev's rule or the empirical rule. Now we're going to talk about the empirical rule part of it. Okay. For a normal distribution with any mean, I don't care what it is, with any standard deviation greater than 0, one can show for a normal distribution that this probability is 0.95. So this is a very high probability of being within 2 standard deviations of the mean. If you go to 3 standard deviations, wow, look at that, 0.9973. That's pretty remarkable. This is what's referred to as the empirical rule. Now, how do I know this? Why does this work actually for any mu, for any sigma? We'll see that shortly. But what you can do on your own, plug in a mu, plug in a sigma, use the Pnorm function, and you will see for any mu, for any sigma, this holds. So a quick question here. Suppose y has a normal distribution. What's the probability y is equal to the mean? Well, again, y is a continuous random variable, so that probability is 0. Okay. At the very beginning, I was talking about this standard normal probability distribution and how this is a special case that often has some important meaning to it. And one of the main reasons is because before there were easy ways to calculate these probabilities using a statistical software package, people would use tables that had all these probabilities in it. And these tables were specifically designed for just one normal probability distribution, the standard normal. I am not going to ask you any questions about how to use the standard normal probability distribution table, but there will still be people who like to use it. In fact, it's still in most introductory statistics textbooks typically. And so because of that, I just want to really briefly show you how to use it. Now there's different forms of the table. I can't show you all forms, but if you know one form, you can pretty much get the other forms as well. And so with the help of R, actually I constructed part of the table here. And let's say I want to find the probability a standard normal random variable is less than negative 3.41. And what I would do with this particular table is I find negative 3.4 on the left-hand column, and then find a corresponding another column that has 0.01 in it. So notice if I were to take negative 3.4 plus 0.01, I get negative 3.41. And then I match up that row with that column, and I get 0.003, and that's your probability. Let's look at one more example. Suppose I want the probability z is less than negative 2.57. So I find negative 2.5, I find 0.07, I come over to match up the row and the column, and I get 0.0051. That's how people used to, and still some do, find probabilities associated with a normal distribution. Okay. Now, of course, we could just simply use the Pnorm function using the mean equals 0 and SD equal 1 arguments. Note that that is actually the default values for this particular function. Okay, so why could we just use a standard normal probability distribution? You know, suppose we have a mean that's different than 0 or a standard deviation that's different from 1. How is that table going to help? Well, the reason is because we can convert any normal random variable to a standard normal random variable by using this little transformation. Suppose y has a mean of mu and a standard deviation of sigma. If I take y minus mu, take the whole thing divided by sigma, I get a standard normal random variable. You'll see me use that in a second. But remember, this z here has a standard normal distribution with a mean of 0, standard deviation of 1. Why does this transformation work? Well, here's a partial explanation of it. Remember how we looked at something like this before. Expected value of a times y plus b, where a and b were constants. And we showed that a times expected value, that this is equal to a times expected value of y plus b. Suppose we put mu in there for expected value of y. Now look what happens if I instead looked at this, y minus mu. I can then rewrite this as expected value of y minus mu. In other words, 0. Combine that with sigma. You're still going to get 0. So that's why z has a mean of 0. Let's instead look at this. The variance of a times y plus b that we looked at before. And we show that that's equal to a squared times the variance of y plus b, or a squared times sigma squared plus b. Let's apply that now to this particular situation. So a here is going to be 1 over sigma. B here is going to be minus mu over sigma. And look what happens. I get 1. As I was doing this, I just noticed I had a little small error here. This b actually, if you remember, disappears. And so that's why I get a value of 1 there. So let's look at one more little simple case that corresponds to this. Let's say I want to find again the probability y is less than 23, but now using this little transformation so I can work with a standard normal random variable. So what I can do is subtract mu from both sides inside that probability, and then also divide by sigma on both sides of that probability. That's not going to change anything because I'm doing it to both sides of the inequality. Well, what is y minus mu over sigma? Well, that's our z. And if I were to actually put in the values of mu and the corresponding value of sigma there and do the math, I get negative 2.16 approximately. Go to my table for actually negative 2.17 if I round, and I get exactly the same probability as what we got before. Okay. Next, well, what does a sample look like from a population that can be characterized by this normal probability distribution? And so let's actually have R simulate a sample for us in much the same way as we've done in other cases. So let's say I take a sample of size 1,000. Very often we use always n to denote our sample size, little n that is. Mean of 24.3, standard deviation of 0.6 for this normal distribution. So the first thing I'm going to do is set my seed so I can reproduce my results. And then I'm going to use the Rnorm function to actually simulate the sample. Again, R basically stands for random. It helps me take my random sample from this population. The first argument, n is equal to 1,000. Put in my mean, put in my standard deviation. So the very first value that I get in my sample is 25.34. Next one's 24.76, and so on. Well, let's take the sample mean of those 1,000 values. Let's find the sample standard deviation of those 1,000 values, and guess what? Those values are very, very close to what we had for the expected value of y, mu, and the variance of y, sigma squared, that we had before, or think of it as sigma, the square root. And so, again, what this is helping us see is, what does it mean for a population to be characterized by a particular probability distribution? Also, how about we take a look at all my values of y and compare it to 23? If we've looked at cases like this before, when I take y less than 23, what R does, it does a logical comparison. If a particular value of y, one of these 1,000s, y's, is less than 23, it returns a true. Otherwise, it returns a false, and does that for all 1,000 y's, or 1,000 elements in y. Then when I try to do math with these trues and falses, like sum or find the average value, it turns these trues and falses into ones and zeros. And so if I take the mean of here, then the proportion of these y's that are less than 23 is 0.015, which essentially matches what we had when we were doing the calculations with the normal distribution itself. How about we do a histogram of all these values? So I can use the hist function. And like what we've seen before, I'm going to rescale my y-axis so I can actually plot the probability distribution on top of it. So I say freq equal false. And then using the curve function, I can plot my corresponding normal distribution and look at how well the distribution, or the histogram I should say, corresponds to my probability distribution function. We can also do a similar thing with a CDF. Hopefully you remember before, when we found the empirical CDF, we can plot it with the plot.ecdf function that we've seen. I can also then plot my CDF itself by using the curve function with Pnorm, put a nice little legend on it, and look at this nice agreement between the empirical CDF and the CDF itself. So we have some questions here. I would like you to answer these on your own. These correspond to questions similar to what we've had before, in terms of what would you expect to have happen with the sample mean and that sample standard deviation if we were to increase the sample size. Well, how valid, though, is it to have a how valid is it to have a population that can be characterized by a probability distribution? And the answer is, it depends. First of all, let's think about what would happen if we got it wrong. Suppose the probability distribution was not normal. And so let's say that instead we had something that looks like this. This alternative distribution in what's kind of pink there, which is actually a uniform probability distribution. And let's say again, I want to find the probability that y is less than 23. So there's 23 right there. And we can see that with the normal distribution, that probability is going to be small. But if instead this distribution in pink was actually the valid distribution, we can see that that probability is going to be much larger. So what if we get this probability distribution wrong for the population? Well, you're going to have wrong probabilities that you're going to calculate. So you might be wondering, well, again, how can we verify that a population can be characterized by a particular probability, by a particular normal distribution? That's where you go take your sample. You do the histogram. You plot the normal distribution on top of it. Do a similar thing with the ECDF or CDF. From that, you can make a judgment of, yeah, this population looks like it can be characterized by this normal distribution if the histogram follows the PDF. If it doesn't, then says, okay, that says you're going to have to try something else. Well, what can you do? What else? Well, there's other probability distributions out there. But there are also ways where instead of working with, let's say, y itself, suppose instead you work with the sample mean of the y's. And in that particular case, as long as you have a large enough sample size, generally speaking, let's say 30 or more, you can still work with a normal distribution, but now with y bar, that sample mean. The reason why that can be done is through what's called the central limit theorem, which is something that we will talk about soon in our course. So with that then that it concludes this section on the normal probability distribution.